So thank you everyone for being here today. We are pleased to have Professor Alexander Renkl from University of Freiburg speaking about studying worked examples in mathematics to relate procedures to principles.
Oh, that's my turn. Okay, thank you very much. Thank you much for the introduction, for the invitation, the opportunity to share some of the thoughts and research we do in Freiburg, and together, of course, with a lot of colleagues all over the world. So the title, you can read it, Studying Worked Examples in Mathematics to Relate Solution Procedures to Principles. And if I talk about examples, I should first show examples, what I mean with this worked examples. Let's see if I can. Well, this is one type of worked examples we used, for example, in research. It's about probability calculation. And you don't have to read the problem text. It's one of these probability problems where related on whether the order is relevant or not, or whether events are replaced or not, things like that. And the goal was especially is to understand why you multiply. Do you see my cursor?
Yes, yes, we can see.
For example, you multiply this fraction, but this means also that you multiply the denominators and so on. And to really understand why you multiply and do not something else. And this can be, for example, done by integrating this graphics or this tree diagram, this solution, numerical solution. And these are also self-explanation prompts, so that the students have to type in here, especially the questions. Why do you calculate the total acceptable outcomes by multiplying? And above there were former answers of the students. So it's not about just the solution procedure, but understanding the solution procedure. Or this is from Bethany Riddle Johnson. Maybe you also know her from the literature, where she provided two worked examples with two different solution methods. And it's also about more, not just doing the solution method, but describe the two ways that these student solutions are different, and what must be given or true about an equation for Patrick's way to be easier than Nathan's way. Patrick's solution is much shorter on the right side. And yeah. Or this is about fostering a number sense of students, younger students. This is also comparing correct and incorrect solutions in worked examples, which is also a usual method. And you see that they should make a note where the 0.15 should be placed on this number line, and Matt makes the correct mark, but Justin makes an incorrect mark, and they provide also explanations. And then the learners should also be prompted to self-explain what's going on here. How is Matt's way different from Justin's way, and why can't you solve the brain? Why can't you solve the problem Justin's way? Or this is German, but it's not important that you read the text. I just wanted to show that we did not only research with algorithmic solutions, but also with fostering students to find arguments in mathematics. I mean, with mathematical argumentation in this context of finding the proof, except for the formal write down of the proof, to get to the proof idea, and to provide a verbal justification for for the deductive steps, for the logical steps, without writing it formally up. And what you see here is the first page of a longer, of a several page worked out example, and the heuristics, how to get to a proof idea and how to check this proof idea are made salient to the learner by introducing two characters, Florian and Nina, and these two characters discuss with each other so that the usually covered cognitive processes can be uncovered. And this is that Florian and Nina try to prove that opposite angles in a parallelogram are of the same size. And also here we have this self-explanation prompt. After some sections of this very long worked out example, students are asked, all the students that are intended to learn about proof finding, about generating proof ideas, what Nina and Florian have just done, which phase of the proving process would you assign it? And then they were introduced to several moves that you can do in this endeavor to find the proof, and they should provide reasons for that. So I think it's clear that worked out examples are here not just used for showing how a procedure is done, how it is done. It's more about why and what are the principles behind this, like a mathematics theorem or certain heuristics in proof finding. And you see also that we often work with self-explanation prompts in order to prevent the problem that the learner study a worked example, says to him or herself, easy, logical, that's the way the problem is solved. But if they should half an hour later solve a similar problem, they have forgot everything and didn't really understand the solution. So it's about understanding the solution. And you might, as a third point, also get an impression what type of mathematics I'm talking about. I'm not talking about mathematics that math majors learn at the university level. I think that's the same in Germany as well as in the US. They do totally different things than these things. Yeah, so this was just the intro to get an impression what I mean with worked examples or learning from worked examples. And the overview of the upcoming is why use worked examples in terms of what is the theory, the theoretical rationale behind it, but what are also findings. Then what learning goal can be pursued by this. I want to go a little bit into detail. And third, I would never argue that just to example-based learning, I use it in a synonymous ways, example-based learning or learning from example from worked examples. You can also spoil it, definitely. I know quite well how to spoil it, but how can you assure the effectiveness of example-based learning? And maybe some final suggestions for practice in the end, some loose prompts for further thought. So learning, the basic idea is often are students introduced to theorems or principles or something like that, maybe in mathematics or in physics. And before they have really understood these principles, they are required to solve problem. And what do then many students do? They use superficial strategies like, yeah, I take somehow the last formula we had in our classroom, or I take this problem that might be similar to the present problem and I copy and adapt the solution procedure. Copy means I take over the solution procedure and exchange, adapt the numbers or something like that. Somehow they try to get to the right numerical solution. That's their main goal. And the argument that proponents of example-based learning make, it might be better to self-explain worked example to assure some understanding of principles and how they can be applied in problem solving before you proceed to problem solving, because then you can make meaningful problem solving, not just juggling with formulas or somehow use superficial strategies to come to the correct solution, but that you really think about math issues or in physics about physics issues when trying to solve the problem, so more meaningful problems. So summary of the main reasons for first self-explaining examples before problem solving is fostering a learning orientation instead of a performance orientation, so that the learner should mainly concern about understanding this stuff and not be so much concerned about finding the right numerical solution to a problem, and then everything is fine. And to assure a basic understanding of the principles and how they are applied to enable domain-related or math-related reasoning by problem solving instead of just superficial strategies. And these superficial strategies would impose unproductive extraneous cognitive load that might hinder cognitive activities devoted to understanding. So the classical study, I mean, there are meanwhile many more study, and not only in math, in a lot of domains, is as follows, and this should show what is meant by example-based learning. So first, the principles introduced in relatively shortly, but it should also be clear what it is basically about, like a theorem one or several theorems. So it's not inductive coming to the theorem or principle, but it's a deductive thing. Then in the control group, the upper line, there's also one worked example, but then the students engage in problem solving. Whereas in the classical studies, after the first example, there are example problem pairs, and this example problem pairs should assure understanding before you go over to problem solving. Meanwhile, there are a lot of studies. Some studies use example problem pairs, but you can also use examples only. And I show you later also how to structure the transition from a more example-oriented learning phase to finally problem solve. But in the end, you should, of course, learn to solve problems. And what was the finding in the classical studies by Sveller? They were typically with 8th or 9th grade students and equation solving, and they needed less learning time, less time for working on the final test where the learning outcomes were assessed or learning success, and less errors in the final test. So do not always find all these three advantages at the same time. So I did a lot of studies in this area. Sometimes you find just that it goes faster and the learning outcome might be comparable, or the learning outcome is superior, but there's no time advantage. But in the very positive case, it can also come out like this. And there are a tremendous amount of studies meanwhile. So, but for which learning goal exactly? Because you're always in the danger if you give a talk on a learning method that people might believe that you, the one who gives the talk, believes that the learning method is the silver bullet or the magic thing. I don't not at all believe in that. I think mathematics instruction may have many different learning goals. I don't want to get through all these things. You can scan over the list, and I think the initial cognitive skill acquisition, and is what I was talking about, is just one goal, and that means that you begin to learn the cognitive skill to solve a certain type of mathematics problems, or physics problems, or biology problems, depending on the domain. And I think the typical form for which typical learning goal for which learning from worked out examples should be used is this initial cognitive skill acquisition. It's not a magic bullet for everything else, at least not automatically. And the basic ideas of my metaphor, so to say, is in which I think, what should the student's knowledge look like? Ideally, the students have a principle represented in memory as a schema to which they can map single problem cases, single problem tasks. And if they have this well represented, they know how a principle or theorem can be instantiated or used to solve a case problem. And on the other side, they also know if they encounter a case problem, they learn to interpret in the principal ways. That means, for example, they can see, this is a problem where the multiplication rule in probability applies. And the principle represented the schema means that they understand, that the P of A or the P of B can represent different things, can represent marbles or whatsoever in different problems. They are not just have superficial knowledge where they think that A or B must always be certain things. And if students are very good, that's more the expert way. They directly see in a transfer case, in a transfer problem, that has to do with the multiplication rule in probability. Ideally, students learn that, but learning by example cases, and maybe not just case A and B, but maybe much more. So having a lot of example cases represented in memory, and there's a lot of literature from analogical reasoning research that says that students also encode the example cases. Then you have a second way, namely you say, the transfer case, that reminds me, or is so similar to this case B or this case XY, and the XY case was related to the multiplication rule in probability. And so you come by this deviation, but this fruitful deviation, to the idea what the problem behind the transfer case is. And though, but you have only this advantage if a lot of example cases mapped to the principle. By the way, why are there 3 arrows between example case A and the principle? Because I want to say it's not that a student just knows, case A, that must have something, somehow to do with the principle X, but that they can really explain in details 3 arrows what the mapping is between the example case and the principle. Yeah, and what is the way, so to say, shown I've told that verbally, but in different terms, more with graphics, to come to this knowledge, to this type of knowledge. Principle is represented with many more than 2. I just took 2 for simplicity. So first you have introduced a principle as a fact, as I said. So they don't really understand it. Of course, if you introduce the multiplication rule, it would also say, imagine there's a dice, you throw it twice and so, but just a minimal amount of very simple examples. But then you get a first worked out example case and a self-explanation prompt who encourage you to make a mapping, a precise mapping between the example case and the principle. And if you have several example cases, the fact comes to schema. So the schema says that there are abstract slots where different concrete the principle as schema means that the principle is represented with abstract slots that can be filled in by concrete features of an example case. By the way, do you understand my English, my microphone, and everything else? Yeah, okay. So you end up with this, that's the basic idea. Assuring the effectiveness of example-based learning, I can make a whole lecture on that, but I give you a glimpse on that. For example, there can be the problem that the learners just superficially process the examples. I know it from myself that I sometimes as a student, often I read work solution steps and I thought, yeah, easy, clear to me, but it was not at all clear to me half an hour later when I should solve other problems. And examples can be too difficult to process, especially in the beginning. I show example why this can be the case. Or examples may not fit the learner's skill level. For example, I said it's for initial cognitive skill acquisition. Maybe if they are proceeded already, I annoy these people with redundant worked examples, and instead it would be better because they have understood the basic rationale to give them problems to be solved. So let's go to these 3 points and remember, to prevent superficial processing, we give this self-explanation prompts. We can also say that's a self-explanation prompt. That's a self-explanation prompt. But one new example, we also had once a cooperation with Carnegie Mellon University. Maybe, I don't know whether you are familiar with the cognitive tutors. They are used in quite a number of US schools. This is a little bit of German on this screenshot because we had translated versions here. But in principle, that's a US product. And it's an intelligent tutoring system, so that has an idea how far the students are proceeded or not proceeded, and depending on this evaluation, so to say, certain hints are provided or certain tasks are selected. And we also once did studies whether enriching such cognitive tutors, which were initially just learning by problem-solving environments, by worked steps, is sensible. It is sensible. And there are also self-explanation prompts. Maybe you can read here the German word Grund. It would translate into English like justification. And what the students had to do to say the geometry rule that applies in this case. And if they can't remember it, they can open a glossary and look out or search for the correct geometry rule. So it's also implemented in this cognitive tutors from Carnegie Mellon University, or Carnegie Learning is, I think, the company that sells this stuff. So that's one way of preventing superficial processing. You can also do other things like trainings. We also have little training modules for students to learn to be good self-explainers. That's also possible, a training, but prompting is easier. examples too difficult to process, I show you something that is from also classical studies, old studies by Sveller, who was once surprised to find another worked example effect in the following case. When the solution was in a split attention format or diagram. I mean, that's the usual way also we do it in Germany. And but somehow the worked example effect reappeared if you used the integrated diagram that made it much more easy to map the equations to the figure, to the triangle. That's why I call it the easy mapping principle. So the difficulty in this thing is that students do not map these two things to a sufficient degree. Initially, it was thought that the reason is that students have much troubles in mapping the lower equations to the diagram up there, and maybe they would show a lot of eye tracking if you recorded transitions. But that's not necessarily the case. The problem is also that it's not an invitation to integrate if you have two separate sources. And actually, sometimes they show very few transitions, too few transitions, and they don't map. And the mapping is better here. It's called not, so the split attention effect, don't know whether you know that name, an integrated format effect is from cognitive load theory, which Mayer would call it spatial contiguity effect. But I don't think that's also a special case. It's more about the easy, whether it's easy to map or not. Let me show this. This is very hard to make an integrated format because these 20 branches correspond to this 20 in the denominator. How should you make an integrated format? But you can ease mapping by color coding. And I have here just a temporary glimpse, a temporary picture of the screenshots. Here is everything blue, but you see there's also green acceptable outcomes. And in later phases, when you study these worked examples, you can also see what the acceptable outcomes are in green. And so you don't have to necessarily make an integrated format, but somehow you have to help the students to know what belongs to what and to invite them to map it by color coding, by integrated format, or we also try to design these questions, the self-explanation questions, in a way that are more or less forced to integrate if they want to answer it correctly. So that's the easy mapping principle. And if it's hard to map, then worked examples can lose their effectiveness. And it might not always fit the learner's skill level to an optimal amount. So we had initially some studies where we thought, how do you come from example study to problem solving? So to just decide, I provide 5 examples and then go on with problem solving or what? And then we had, it's more schematic here. We had an example phase, and let me begin. Our control group was example problem pairs. That's already a strong control group because that's what John Zweller did in his worked example condition. And we thought it might be more sensible to fade the solution steps. So take a similar example. The example had 3 solution steps. And then the next example, there are two steps worked out, and the last step has to be found on the students have to find it on their own. And then the next faded example, the first solution step is faded out, and then it's have to do 2/3 of the problem on their own, so to say. And then I come to problems to be solved on their own. That provides a smooth transition. But we used also, it's the Salden et al. Study, for example, the cognitive tutor, intelligent tutoring technology to make an estimation how far proceeded the learners are. If they provide correct self-explanations in this field where justification was written, or Grund in German, and they can make it quickly, then we said, probably he has understood this type of solution step more or less in terms of the underlying principle. Then the next time when they encounter such a problem step, they have to do it on their own. We have an adaptive fading. If you have difficulties in self-explaining, you had a lot more worked out steps, and we faded out those worked out steps where they did good self-explaining, fast good self-explaining. And this was a good idea. At least it had good effects. And that's a way that we really try to tailor the worked out example methods to the student's knowledge level, so that it goes in the right way to problem solving, depending how fast they are proceeding in skill acquisition. We go faster to problem solving if they proceed slower in skill acquisition. They study more worked examples. Yeah, so I'm much faster than I expected. I hope I was not too fast, but you have time to ask. So some final practice recommendation, not strict recipes. I don't think these are sensible to provide recipes, but just some guidelines where you might think about. And you might consider using example-based learning when students should understand principles and the application. Maybe after reading some more papers, I will have also, you can have the slides, of course. I will show you some literature on the next slide. And I say consider because I do not believe that example-based learning is the one and only way where you can do it. There are also methods based on analogical reasoning where you have more example cases, 2 or so, and whether they try to bring the students to abstract the principle. That's also a possible way if you structure it in a good way. That's an easy way. But I think it's not a bad idea, at least, to use example-based learning. And what can be an error if I was giving talks, for example, in Germany, also in research group with subject matter educators. They often constructed also worked examples, but they could not always say exactly what are the one principle or related principles. Maybe I want to say also, if you have a proportional reasoning problem, it can be proportional. The more miles you do, the more gas you need, but it can be also anti-proportional. The more pumps you have, if there's water in your basement, the less time you need. And sometimes students have difficulties in differentiated that. Is that the goal, that they should differentiate that, or should they get an idea about heuristics of proof finding? I think you should be rather exactly what you want to teach with this worked examples, and then give a short introduction on these issues, on these principles or related principles. And it's also important that the students are able to remember these principles. If I provide later on self-explanation prompts where they should relate the problems at hand to the principles, and they don't remember the principles, it's not possible. So often we made a little in between tests to see whether they have really encoded the principles taught initially and made a little bit of reteaching, so they really can remember that. Otherwise, they cannot sensibly self-explain later on. And find good examples in the internet or in your colleagues' bag or whatsoever, or you have to design them and check the difficulties that these worked examples might pose to the students and try to make it easier. They should not be distracted by complicated numbers, by unknown words, or by difficulties in mapping different representations like graph and equation. So as I said, and I would, in the beginning at least, try to make it relatively easy in these terms and prune difficulties, so to say. And one issue that I often have with teachers, I think it's important to assure that all students engage in self-explaining. If I go to high school teachers and give such a talk, often they say, uh, um, this is an old story you tell us. I always use self-explaining prompts in my class, and I say, yeah, how do you do it? And then they say, I ask the class why. Why is the solution how it is? But what happens usually, I think American classes are not different from German classes. There are, let's say, from 25 people, there are these 5 math tracks, and they think about the why, and they raise their hands, whereas the other says, let's wait for the others, and don't really think through. But that's not the way it should be. That's why we often also use these written boxes so that everybody is encouraged to write something down. And what my feeling is, at least also as a university teacher, if I have good ideas what I do in a seminar, it almost, and if I take literature on justifying what I'm doing, it all, as good as always, it doesn't work the way I intended, or it just worked to 70 or 80%. So it's always good to let the students leave traces to check whether they can do the self-explanation. For example, that you scan the students' entries in the self-explanation boxes to see whether they can actually provide correct self-explanations. It's also a finding that we found, in contrast to Mickey G's assumptions, who is the one who invented self-explanation concept. Wrong self-explanation can also actually be detrimental. So let students leave traces to check whether they can really do it. And it might be too difficult. What we did when it was very difficult, sorry if I go back, it is more this self uh, this self-explanation prompt is very difficult for high school students. And what we did then in a first run through these examples, we made a text with is it what is the English word, a closure text, or with text with gaps in it. And this is a type of scaffolding for the first self-explanation prompt. So there was almost a self-explanation that had to be supplemented, so to say. And only in the next round, it was this empty box. So if it's too hard for them, make it somehow easier, or you can also give them options in initial self-explanation. Is it this explanation, this, or this explanation, and why? So that they should be successful and only later make it more difficult. And as I said, at least it's the way I feel it's always with teaching. If I try something, I have always ideas how to optimize in the next round, because it never works in the first round in just the way I wished it worked, I hoped for. Yeah, so this is a biased literature list, of course. There are some of papers which are uh, I think it's not a single empirical. These are all overview papers, and maybe not. Maybe the Renkl 2014 is rather more difficult to read, but the Renkl 2017 is out of a math education journal, and the Renkl 2023 is more for the broader audience. And there are also other handbook things which are not too difficult to digest. And I also like the Bethany Riddle Johnson's meta-analysis on promoting self-explanation to improve mathematics learning, because I think self-explanations prompts go quite well with worked examples, because I have the cognitive capacity available to concentrate on these self-explanations. Whereas if I combine it with problem solving, then I might be more twist between getting to the right number, or should I understand it, or if I get to the right number in the first place, do I still have to strive for a deeper understanding that might not, for us it's clear, but for the students they have very often different answers than we have. Yeah, I'm looking forward to your questions, and probably you have also question marks in your head like this friendly colleague here.
Thank you very much. Does anyone have any questions? I have a question myself. You mentioned relating problems to principles. My experience has been that students usually, as much as possible, they want to avoid learning principles, and it's easier for them to just learn the examples. And so what happens is, if I give them a similar example to what they have seen, they're able to solve it. But if I ask them, okay, can you explain the principle now? They don't know the principle, but they can solve the example. And if
Yeah,
I give them a different example, then they cannot solve it.
yeah,
Uh, is that
yeah.
uh, is that something like it's like a human nature that they try to? It's easier to learn the examples and more difficult to learn the principles.
Yeah, some people have the pessimistic attitude that humans are cognitive misers, that they don't want to spend unnecessary mental effort. But on the other side, I think one idea is with example-based learning is to take away the solution task, so they have nothing else to do instead of caring about what is the underlying principles. That's so the trick. And maybe one has also, of course, to this is I don't know whether this is the correct English word, to flanker, or to as a side additional help to do other things like um, what do you ask for in your tests or in your exams or so? If you would ask them also to explain, then there would be a better a constructive alignment in the sense of BICS. Maybe you know this model. And also, actually, when we made so informal school projects where we introduced in school subject in mathematics worked examples with self-explanation prompts, often so more informal observation. But the teachers often reported that one of the first questions was from the students, yeah, in our tests later, do we also have to explain the solution steps? And the answer should be, of course, yes, because then it's more difficult to avoid to go the understanding route, I think.
Okay, thank you.